Alright, well hello everyone. Welcome. So, 2 weeks of spring break, we'll start some more magnetism stuff today. Do more magnetism stuff next week. Reminder, y'all's test is after spring break. So the Thursday following spring break is our next test. Then we'll have 3 weeks of fun. We'll do light, we'll do optics, we'll review, all that good stuff. And then we'll have our exam at some date that I posted in the syllabus. You can also look up any of your dates. So last week we talked about magnetism. Specifically, we said magnetism was discovered because moving charges experience a force due to something. And that something we said, it's a magnetic field. And then we did a bunch of things on it. We said the force in a moving charge was Q VB sine theta. We said the force on a current carrying wire was ILB sine theta, where B is that magnetic field. And then we ended the class a little bit kind of in a rush, last 2 minutes, kind of for a cool punchline that honestly you don't need to know, but it's cool. So I've told you all magnetism is super important. And last class, in the last 2 minutes, kind of showed a really important one, which is basically electric motors. Now, when people think of electric motors, they probably think of electric cars nowadays. But literally anything that moves that's powered by electricity, anything that moves that's powered by electricity is an electric motor. So it's far more than just electric cars, like a blender that's got an electric motor in it. Gosh, what other things? A hair dryer. That's a fan. A fan is an electric motor. Anything that you plug it in and it starts moving is an electric motor, and this is how they work. They have magnets in them. Your speakers and your headphones, they're not quite electric motors, but they also involve magnets and electromagnets, and we'll talk about that at some point. Anything that moves that's powered by electricity has magnets in it. They're extremely important. So last class we kind of finished off with, hey, we had a loop of wire, and the bottom of the loop experienced no force, the top of the loop experienced no force because the angle between the current and the magnetic field on the bottom is 0. The angle between the current and the magnetic field at the top is 180. Sine of 0, sine of 180, it's 0, there's no force. And then at the very end we kind of said, on the right side there's a force that is into the page. On the left side there's a force that's out of the page. If you have a loop and one part's getting pushed one way, one part's getting pushed the other way, it rotates. And that's literally all an electric motor does. So it's pretty cool. Something that's important is you do have to kind of flip it. So there's tons of videos of these things. So this is me. This is so weird. I don't know if I am streaming a YouTube video. I don't know if this will get in trouble or whatever.
Very basic construction.
Oh my gosh, it's got noise. Go away, noise. All right, so a loop of wire. This is like the simplest. Now they won't look as simple as this, and we'll talk about why kind of as time goes on. But this is one way of doing it. You got these permanent magnets. You run the current through it. This little loop we'll talk about in just a second. This is called the commutator. Really fancy word. But when the current is going one way, you get these magnetic field lines. Remember, they go north to south. And it causes a force on it. So at this point, current's going to go this way, flow through it that way, and you get a force that rotates it one way. Now this commutator, the reason that's important is when it gets halfway through its rotation, we need the current to flip directions. So then instead of the force continuing to push it this way, because at some point if we didn't flip it, it would just kind of do a 180 rotation and then stop, and it would get stuck there. So to get it to do the next 180 rotation, you flip the current, and you all can look into that. There's so many videos. It's it is really interesting. I'm not going to spend too much time. I'm not really going to spend any more time on it. But this is so that we flip the current, so that after it does that 90-degree motion, it'll keep spinning, then the current flips, and then that'll keep it going, and then the current flips, and that'll keep it going. So you have to keep flip-flopping the current back and forth so that it actually keeps spinning. It doesn't just lock up. Anyway, this, and then this connects to how to make this thing do it. So this thing literally rubs up against these. If y'all have ever heard the term brushless electric motors or brushless, and then I guess the other ones are just called brushed. I don't know if you call them. This one is one with brushes. Literally, these are brushes that rub up against this piece of iron or this piece of copper. Notice how that copper spins against it. Fleming, left hand. No idea what left hand rule is. That's weird. But brushless motors don't have these contacts. They have another way of doing it. Feel free to look those up. But just wanted to mention that to y'all. We kind of got through the last 2 minutes. You don't need to know it. You do not need to do the math for it. But it is just super, super applicable. Literally, anytime you all plug something into the wall and it starts moving, there's something like this probably going on. Headphones is a little different. We'll get to those when we get to those. But we'll learn about how headphones work on for next week. So, anyway. So I just wanted to kind of mention that because it is so important. So today, we talked about that magnetic fields cause forces on moving charges. So next question is, how do you get magnetic fields? Permanent magnets is one way, but it is not the only way. They're both useful, but how do we get magnetic fields? Okay, so previous things you need to know, it's the same things as last time. Vectors, you don't really need to go cross product. You need to know that current is defined as the direction that positive charge is moving, even though it's not the actual case. You need to know what a magnetic field does, and you need to know that there is forces due to magnetic fields. Again, basically what we talked about last week. All right, we're going to learn that wires make magnetic fields. That's basically this entire thing. So, to that end, how do we kind of understand that? So I want you all to, I'll read through these, see if you can come up with the answers to these. So what generates gravitational fields? What makes gravity? What experiences a force due to gravity? What makes electric fields? What experiences a force due to electric fields? See if y'all can come up with the answers for these. The second part's a nice review. The first part is something from Physics 1, but something that most people know, even outside this class. Spend a few seconds, think about this. Because if you can understand this, then the next thing I'm going to tell you isn't going to be anything crazy. So, what generates gravitational fields? You may think of a bunch of objects. The Earth, the Sun, all sorts of things in the solar system. What do those things have in common? Mass. Literally every single object that has mass in it, any object that's made of something, makes a gravitational field. Oh, what's affected by things with a gravitational field? Mass. The things that make the field experience the field. All right. What generates electric fields? Charge. What experiences a force due to electric fields? Charge. The things that make the field experience a force due to the field. So, let's just apply that to magnetic fields. Which of the following will generate an magnetic field? Pro tip, it's the one that experiences a force due to the field. Whatever makes it experiences a force due to it. That's true. I mean, these are the only 3 types of fields, but they all follow the same rule. The things that make a field experience a force due to the field. So, do you remember from last week, what experiences a force due to a magnetic field? Is it stationary charges, moving objects with mass, or stationary objects with mass? We'll just go to 50 seconds. It's one of those you know it or you don't. I mean, I guess you could be looking up the stuff from last time, which is fair. All right, we'll close this out in 5, 4, 3, 2, 1. All right, so this is just basically a review of last week. So what generates a magnetic field? The things that experience a force due to a magnetic field. What experiences a force due to a magnetic field? This was the equation for it. You need a magnetic field, you need a charge, and you need that charge to be moving. If a charge is not moving, it does not experience a force due to a magnetic field. It'll experience a force due to an electric field, but this is how they discovered magnetic field. They saw that once it started moving, it did things that the electric field didn't explain. It did things that the gravitational field didn't explain. So they're like, there has to be something else. Hence the magnetic field. So the thing that experiences a force is also the thing that makes the field. And that's literally what this entire PowerPoint is. Let's calculate how strong of a field we can make. Now the next slide, I warned you all, we did right-hand rule. It was called right-hand rule number 1. I would not call it right-hand rule number 1 if there wasn't a right-hand rule number 2. There's no point in numbering them if there's not a second one. So, moving charges make magnetic fields. That's literally this entire PowerPoint is just walking through that. Moving charges make magnetic fields. What do we call it when we have a bunch of moving charges? Current. Current is literally a bunch of moving charges. And we define it as positive charge moving, even though that's not the reality. And what I really want to highlight before I even start teaching right-hand rule is this picture down here. This shows the magnetic field due to a current carrying wire. And it may be a little tricky to see, but what's happening here is these magnetic fields are going in circles. It makes magnetic fields that kind of go in circles around it. And if we want to find the magnetic field at a specific spot, we're going to go to that circle and we're going to find the tangent line to that circle. If you all remember from Physics 1, like tangential velocity, if you remember finding the direction of tangential velocity, it's kind of like that. Now, I mentioned all that. We're going to use right-hand rule number 2 to do this for us. But if you can understand that it's a circle, you can kind of understand how this rule is working. And you can kind of make sure you're using it correctly. So, how do we use this rule? Let's just pick this spot that I marked on my picture. So we have a current carrying wire where the current is going upwards. And I'm going to zoom in on this. I know it's a very tiny picture here, which is not ideal. So we have a current carrying wire where the current's going upwards. And I said, hey, let's find the direction of the magnetic field to the right of it. It doesn't matter where to the right. The direction will be the same no matter how far to the right. So you point your thumb in the direction of current. So my current's up, so my thumb is up. What we then do is you point to your fingers. I'm going to kind of reword what this has on here. You're going to point your thumb up, point your finger to the spot you care about. So the spot I care about is to the right. And then you kind of got two options. One, you can just straight up say, my palm points in the direction of the magnetic field, which is into the page. Or, I think this may make it a little easier, swing your fingers 90 degrees, and they point into the page as well. Both do the same thing. So, thumb points in the direction of current, point your finger to the point you care about, and then you just kind of point it inward. So the magnetic field at this spot, at its place to the right of it, is pointed into the page. So for those online, thumb up, fingers to the point, swing them 90, bam. Or again, you could just say the direction of your palm. There's many ways to kind of do this. So the magnetic field here is into the page. It's kind of tricky to draw that, but you get the idea. Let's just go ahead and pick a spot out here. Let's pick a spot that's in front of it. So I have my current that's going up. Boom. I point my fingers to that red dot, which is in front of it. And then I just swing them 90 degrees, boom, and it's a straight line to your right. That's it. That's right-hand rule number 2. Thumb in the direction of current, fingers out, swing them 90, it's to the right. It's pretty easy to see. Well, let me rephrase this. It is easier to see when we have all these circles. You're not going to have these circles though when we do problems. But if you can imagine in your mind that these circles are around it, you basically just got to figure out what the direction of the circle. Okay? So, just like before, what do we do now? A bunch of them. How do you get good at right-hand rule? Number 2, you do right-hand rule 2. All right, so one at a time. We got 4 different scenarios here. First one, I've got a current going to the left. And the question is, what is the magnetic field above that wire? So, point your thumb to the right, point your fingers up, and then either the direction of your palm or swing your fingers 90 degrees. It does the same thing. That's the direction of the magnetic field. So, thumb to the left, fingers pointed at the spot, boom, 90 degrees, right into the board. That's the direction of the magnetic field. So above the wire, thumb to the right, fingers up towards my magnetic field, and this is good to remind you all, that's going to be a dot. A dot is out. Oop, did I do the wrong one? Yep. X. X is into the page. Get used to the X's and the dots. Good news, I'm not going to ever give you all negative current. So you don't have to worry about the whole, what if it's negative charge flowing? It's always going to be positive charge. So right-hand rule number 1, we had to worry about if it's an electron or proton. This one, you're only going to worry about I. All right, great. On the bottom, thumb to the right, or left, thumb to the left, fingers point down, fingers swing out of the page. And if you just think about this, remember y'all, there's basically this circle going around this thing. At the top of the circle, it's coming into the page, and then it kind of swings around, and on the bottom it swings out. It's this circle. That's really what we're looking at, is this magnetic field that's a circle around it. We're just picking spots in that circle. All right. The ones C and D. Now I got a current going down. Same thing. This one, at least in my opinion, is easier. I don't know if it's easier, but you can decide. Thumb goes down. Boom. Fingers point towards C. Great. Swing them in. Into the page. So thumb points down, fingers point towards C, into the page, which is an X. The other side is going to be the exact opposite. But good to check it. Thumb points down. Thumb points down. Keep my hand flat, point it towards D, swing it 90. We did it. What is hard about right-hand rule number 2 has nothing to do with right-hand rule number 2. It has to do with now you got 2 right-hand rules and you got to remember which one you use for which. That's how it gets tricky. You now got 2 different things to do. Yeah?
Really quickly, if you go back to the last slide,
yeah.
Can you go over how you did this second one again?
The one that's in front of the wire?
Yeah.
Oh, do I have it the wrong way? No, that's good. Okay, I was scared there. Yeah, so I just pointed my thumb in the direction of it. Pointed my finger. So this spot was kind of in front of the wire. This is where it's kind of tricky to show.
Out of the page.
Yeah, so if this is my wire, the magnetic field is doing a kind of like an orbit around it. So if I'm in front of it, thumb is up there. Yeah. Okay. 3-dimensional stuff is, and that's the unfortunate thing with magnetic fields is we have to work in 3 dimensions because no matter which way current's going, magnetic field's doing a 3-dimensional circle around it. But yeah, thanks for asking though. Okay, what a great question. In fact, here it is again. So, a wire carries a current upward as shown below. What's the direction of the magnetic field at point P? Is it towards the wire, away from the wire, left or right? I will not try giving a picture like this on the test. On the test, it will be much more straightforward. There's a current going up. What's the magnetic direction of the magnetic field to the left of it? I will make the wording as clear as possible, and I am not going to be giving any crazy pictures that have ambiguity to them. I do not want my questions to be a measure of, can you understand my funky English? Can you understand what the heck's going on? Like, they will be as straightforward as they can. A wire carries current up. What's the direction of the magnetic field to the left side of it? It's kind of simple English as I can make it. All right, we'll go to a minute 05. In 5, 4, 3, 2, 1. Okay, so I got a current carrying wire going up, so I point my thumb up, my point's in front of it, so I put my fingers pointing towards it, swing them 90 degrees, and I get, so thumb up, P is kind of away from the screen, swing it, and we get an answer that's to the right. That is the direction of the magnetic field. Not a force. This is literally what's a field. And a field can exist anywhere. All right. Fantastic. Another one. Same situation. Just asking you what's the direction of the magnetic field on the right side of it. Current carrying wire going up. What's the direction of the magnetic field? And my wording here isn't great. Let me just go ahead and clarify for you all. Let me change these. I'm going to change this down to into the page, and I'm going to change this up to out of the page. I think that's a bit better than up, down. Again, I will not do one where you have to be like wording-wise unsure. On the test, your only options will be up, down, left, right, into the page, out of the page. That's it. We're not going to do anything funky. Because it just gets so hard to word and to be clear and all that kind of stuff. Alright, we'll go to 45 seconds. In 5, 4, 3, 2, 1. Alright, so thumb points up, P is to the right of it, so you point it to the right, your fingers curve 90, it's into the page. Thumb points up, P is to the right, swing it in, and it kind of points that, we're just going to call that, again, it's so hard to draw in here. It points kind of along that plane, which we're going to call into the page. Into the page. The reason I drew this whole thing, the reason I put this in this weird way, is what we are doing is just realizing that the magnetic field is making this circle. At this spot, the first spot you all cared about, the magnetic field was pointed to the right. At this spot, it's kind of pointed into the page. Which way does it point? On the back side of it. And it's just this, there's a circle of magnetic field going around it. This magnetic field's making a circle around it. So to kind of draw that same circle again, so it's making this circle. Oh, oops. I was mean. I was so mean. Okay, well, I'm just going to give you all the answer because this one was kind of mean. This one, the current's going down. It looked almost like the same problem, but be very careful here, y'all. This current is downwards. I don't know why Past Me decided to do that. I'll probably change it. You know what? It's too late. It's downwards, downwards, it's downwards. So point your thumb down and then do the same thing. So just make sure you didn't point your thumb up. If you did, you get the wrong answer. Current goes downwards. So I'll give the people online to frantically try to change their answer as they realize it's, well, maybe they realized it. Yeah, it's not looking great. All right, we'll go to 25. But yeah, the current points downwards. My point is behind it. So 5, 4, 3, 2, 1. All right, so you point your thumb down, the spot's behind it, you swing at 90, it's to the right. The magnetic field is to the right. Thumb down, for those online, swing at 90. And just, yeah, make certain when you're swinging your fingers, you don't overswing them. Again, if you want to be safe, just use your palm. If you point your thumb down and you point your fingers towards B, your palm points to the right. That's kind of that's a safe way of doing it. Okay. And because I want to be really mean, let's give you all another, well, remember I told you all the hard part isn't necessarily right-hand rule number 1. The hard part is now you got 2 rules and you need to make certain you don't mix them up. So, an electron is moving upwards in a magnetic field that's pointed into the page. What is the direction of the force on the electron? Is it, so boom, and gosh, I even have to switch my brain on this one. Is it right, left, up, or down? So you just did right-hand rule number 2. And your brain was in right-hand rule number 2, but this is the challenge. Can you go back and forth between the rules? Can you remember right-hand rule number 1 now? Pro tip, always draw a picture for these. If I don't give you a picture, draw a picture. If you draw a picture, you can just make your fingers line up to the picture. If you don't draw a picture, you're both trying to line things up and you're also trying to visualize it in your head. You can either make your hand work more by drawing stuff or you can make your brain work more. I recommend making your brain work less because that's the hard part. Oh, I haven't started the question. Well, that's a bummer. All right. Well, there you go. So right-hand rule number 2 was you pointed your thumb in the direction of current. You pointed your fingers at the point and your palm gave the direction. Right-hand rule number 1, your thumb does not point in the direction of the moving charge. Your fingers do. This is what makes these rules hard. Individually, they're not hard. Well, after you do them enough, they're not too bad. At first, they may seem weird. But it's, are you going to mix them up? You got a note card. You can write stuff down. All right, so let's see how we did. It's okay. Most people got it wrong. All right, I'm going to close this out. Now everyone's going to double check themselves. We'll go to 110. In 5, 4, 3, 2, 1. So the reason I gave this problem is, again, I know we're just learning this stuff for the first time, but this is what's going to happen on the test. Is these problems are going to be all mixed together. And that's what makes these tricky, is remembering which one for the right job. So, to that end, let's just go back to the other ones, just to remind ourselves so we can draw the contrast. So for right-hand rule number 2, your thumb goes in the direction of current, fingers point towards it, swing your hand 90 degrees. That's the one we just learned. Right-hand rule number 1, the one we learned last week, your fingers go in the direction of the moving charge. Your palm goes in the direction of the magnetic field. So fingers point up, and then I kind of rotate my hand around so that my palm points into it. Your thumb points in the direction of the force on a positive charge. Your thumb points in the direction of the force on a positive charge. This is an electron. Meaning, the force, so fingers point up, palm is the direction of that. The force in a positive charge would be to the left. This is a negative charge, it has the opposite. Yeah. So, you have to be careful with right-hand rule number 1. Is it an electron? Is it a proton? And hey, if you missed it, you're in great... Oh, hey, people switched it. Wild. It was 40 people here, and then... I guess they... I don't know. But, Yeah, if this was a positive charge, the direction would be the other way. So, anyway, be careful with this. So yeah, if we drew this picture and I made it a positive charge instead, same exact everything, then it would be to the left. So, we have lots of time between now and the next test, and that is both good and bad. This is just one of those things to be careful of. Okay, so great. We got our directions down. Right-hand rule number 1, right-hand rule number 2. Good news for you all. That is technically all you need right-hand rule-wise. I'm going to give you a right-hand rule 2.5 eventually. And right-hand rule 2.5 is just a shortcut for a specific type of problem. You don't actually need to know it, but it can make a certain type of problem easier. We'll get to it when we get to it. But right-hand rule 1, right-hand rule 2, that's honestly enough. There is no right-hand rule 3. So that's nice. Okay, I'm going to show you a slide, and it's going to look absolutely disgusting because it has something that you all do not need, which is calculus. So I'm going to put it up here. You do not need to know most of what's on there. I will tell you what you need to know, but I just don't want you to see this and be like, what the hell is that? Okay, there it is. So what's going on here? The reason I'm showing this to you is we just found the direction of magnetic field. The next question is, how do I find the strength of the magnetic field? How do I actually get a number for it? There is something called Biot-Savart's law, which involves doing an integral. It's as awful as it looks. Like, it's not ideal. Good news, you don't have to do an integral, but I just wanted to show this to you. This is actually how do you calculate the magnetic field due to a wire or a wire of different geometries and all that kind of stuff? You have to do this integral. But because we don't have integrals in this class, you do not have to do this integral. So what is this going to look like then? This is going to look like me giving you the magnetic field. Just, hey, here's a wire, here's the magnetic field for it. Here's a loop of wire, here's the magnetic field for it. Here's an arc of wire, here's the magnetic field for it. We're not going to derive these things because it involves an integral. That's why I'm showing you this. It comes from something that you all don't need to worry about. Okay. All right. This is also a reminder. Remember, if you have a single charge and you want to find like the electric field due to it, fantastic. If you have several charges, you just find the electric field due to all of them and you add them up. The same thing is true of magnetic fields. If you have a bunch of things causing magnetic fields, and we're going to see examples of that. If I have a bunch of different things causing magnetic fields, find the magnetic field due to each something, and then just add them all together. Okay? If something looks super, and we'll see examples of that, but that's kind of all you need to know. And now I'm going to give you the equations for those somethings. What are those somethings? The first case is an infinite straight wire. And again, see this integral? Pretend like it doesn't exist. There you go. That's what you need to know. The magnetic field due to a wire, due to an infinitely long straight wire. It's a very specific circumstance. Will you ever encounter an infinite wire in your life? No. But honestly, if that wire is just like this long, that counts as infinite. Like, it doesn't need to be that long to be infinite. You just got to be close enough to it. Remember the example I gave you all? A wall isn't infinite, but if you get close enough to it, it might as well be. If you can't see the edges, it's infinite. So, how close do I need to get to the wall? This close. I can't really see the edges. It's infinite as far as I'm concerned. Infinite things do not exist as far as we know it, but they can basically be infinite if you just based on approximations. We love approximations. So yeah, magnetic field due to a wire, mu naught times I divided by 2 pi r. And I'm going to look at each of these variables because we have some new variables thrown in here. Mu naught, it's just a number. It's a constant. It is 4 pi times 10 to the minus 7. We're going to see mu naught a bunch. It's called the permeability of free space. You don't even need to know what it means. All you need to know is that every time you see mu naught, mu is the Greek letter, lowercase Greek letter mu. It's a U with an extra leg. That's how you draw it. You draw a U, and then you give it an extra long leg on the left. Greek letter mu. I didn't invent the letter, the Greeks did. It sounds like U, but it's got a mu. M-U. Mu. 4 pi times 10 to the minus 7. Remember, this is that scientific notation. This is just 4 pi times 10 to the minus 7. You just put that number in. If you see this equation, if you see any equation with mu naught, just put that number in. All right, I is the current in the wire. That should be familiar. R is how far away you are from the wire. That should be familiar. Pi is pi. Which, fun fact, we are coming up on Pi Day. How exciting. Certain pizza places have deals. So keep that in mind. There is some relevance to you all. Yeah, and R is the shortest distance. I have to clarify the shortest distance, because if I just said it's the distance to the wire, is it this distance? Is it that distance? Is it this distance? All of those are distances to the wire. So what is R? It's find the spot that's closest to it. Just straight away from the wire. Take the spot you care about, boom, that's R. Straight down. Okay, and you just plug in numbers and you solve. Fairly straightforward. All right, you know what's fun though? I've got a point here. Go ahead and practice. What's the direction of magnetic field at that spot? It's one thing to calculate it. Honestly, that's more straightforward. What's the direction of the magnetic field at point P? This is right-hand rule number 2, so we flip our brain back to that. Your thumb points in the direction of current. For right-hand rule number 2, your thumb points in the direction of current. And I will also tell you all, this is the only... Normally, I guess, I don't know if people check this. I haven't been checking this. I am okay if you all write things on your hand coming into the test. Specifically, I'm okay if you want to write I, B, like if that is somehow helpful to you, you want to write the letter, like, just you got to be careful because in one case the chart, like right-hand rule number 2, your thumb is the direction of current. Right-hand rule number 1, your fingers are the direction of current. If you want to write that stuff on your hand, go for it. I don't care. Like, if that helps you, again, I don't need you all to memorize this. Okay, so thumb points in the direction of current, fingers point in the direction of P, palm points in the direction of magnetic field, out of the board. So at point P, thumb in the direction of current, fingers towards point P. It is out of the board. And I always have to pause and think about that. Okay. Has no effect on the math. Unless you have 2 wires. And you have to add up. So remember when I told you all, let's see, does that show up yet? No. Remember when I told you all, hey, if you have a bunch of things, you want to find the magnetic field due to them, what do? You just add them all up. So what if instead I had 2 wires? I would find the magnetic field in one of them. I'd find the magnetic field to the other one. If the magnetic fields lined up, they add. If the magnetic fields are in opposite directions, one's positive, one's negative. We'll see examples of that, but I'm just foreshadowing it for now. That will happen. Okay, again, if you want to see the derivation, I have a nice hidden slide. It's hidden because you don't need it. Woo, there it is. If you want to know where it came from and you like calculus, and it's gone. All right. So, what is the magnitude of the electric field 3 meters away from an infinite wire with a current of 2A? I don't really like how I wrote these answers because it does mean you have to get a calculator out. I kind of wish I hadn't just put it in terms of symbols, but whatever. This is fine. This is literally just practicing plugging numbers in a calculator. So B, I'm just going to even put the equation for you. Mu naught I over 2 pi R. Mu naught is 4 pi times 10 to the minus 7. So this is just an exercise in trying the equation. Trying it out. Trying the numbers in there. What's cool is in most calculators, you literally can just put 4 pi times 4 pi e minus 7. Ugh, I hate it when I do this. Oh, no, it's fine. It's fine. Whew. All is well. All right. I'll even be caught. Well, yeah. What's the unit? There's technically both the units here are correct, but remember, there's only one unit that we use in this that we've been using for every single case so far. Is it Tesla or is it Gauss? What's the one that we've been using up to this point? That's also what I'm checking if you remember. Pro tip, it's the one that looks familiar. It's a good rule of thumb. If you'll ever see a unit or a word on the test and you're like, I've never seen that before, that's probably not the right answer. So yeah, we'll go to like 215 or something, 220. This is just literally plugging it in. No fanciness here, nothing crazy, no tricks. Just put the right number in the right spot, practicing putting mu naught in, practicing finding the pi button in your calculator. And yeah, making sure you put the right numbers in the right spot. It is possible to mix up the numbers. That can happen to you. All right, so we'll close this out at 2:30. So in 5, 4, 3, 2, 1. Hey, but look, we're getting more people. That's exciting. All right, so let's just make certain we're cool with the variables, because that is, if you're going to make a mistake, that's the first way it's going to happen. I is 2a, r is 3m. We didn't have to convert any of them, so yay. So then you just put them in, so 4 pi e minus 7 times, make certain you put the right thing here. If you put the 3 on top, it's going to give you the wrong answer. Times 2 pi times 3. And you do have to be careful to make certain, either you put parentheses on the bottom, again, it's just small things, but it'll have an effect. Yeah, and we got some different answers here. So this is a good problem just to kind of practice plugging in. You plug this in, and you will get 1.33 times 10 to the minus 7 Tesla. That's just what it turns out. So this is a great problem to kind of just practice plugging in the numbers. Look at all these questions I haven't identified. I'll go back and fix them. Yeah. And that's okay if you mess this up. Like, that's why I gave this problem, is plugging stuff in is part of the process. Because your all's test is mostly multiple choice, that is a thing. And Tesla is magnetic field. I am not dealing with Gauss at all in this class. Okay, you will never see a problem where I ask you about Gauss. It is a unit for magnetic field, but these equations spit out answers in Tesla. So there's not really a reason for us to deal with Gauss. Okay. This is kind of the wording that you can expect to see on the test. What is the direction of the magnetic field if the wire's current goes from left to right and the point of interest is above the wire? Above does not mean out of the paper. Above literally means if you drew this, go above it. Go up. So I'm not going to draw a picture right now because, again, I want you all to draw the picture. You are welcome to try to do this without drawing the picture, but that is the strategy. It's always been the strategy in this class. Anytime you're talking about vectors, pictures are great. It's the first step in the problem. It's step 0 of the problem-solving process. Draw a picture. So yeah, is the answer A, out of the page, B, into the page, C, left, or D, right? I will tell you, for me, like if I was solving this problem on my own, I would draw a picture. Even though I've been doing physics for so long, just because I know how easy it is to make mistakes. I know how easy it is to mix up things. If you have it on paper, if you break it into pieces, it makes your brain work less. It lets you focus on what you need to focus on. All right, we'll close it out in 5 seconds. So we'll go 5, 4, 3, 2, 1. And I could have said here the current goes to the right That's another wording I could have used. So left to right just means it's going to the right. That's my current. Above the wire means above the wire. Not out of, I will say out of the page or into, I'm not even going to use the phrase out of the page or into the page as far as a spot, because that is just not quite clear. So above it is above it. I don't know what to say. North of it. Again, it's one of those funky things. So anywho, thumb in the direction of current, fingers point up, palm points out of the page. There's your answer. Thumb points to the right, fingers point up, palm is out of the page. Out of the page is the direction of the magnetic field here. It's making that circle. Boom. There we go. So yeah, it's just one of those, like the other right-hand rules, practice, practice, practice. You do enough of these, you'll have it down. There's only so many scenarios I can give you on this. Current can only point in so many directions. Up, left, right, into page, out of page. 6 options. And then there's a bunch of points around it you could think of. But okay, so great. Directions, all that jazz. So much fun. Let's do a problem with 2 wires. Told you what happened. Here it is. 2 long straight wires are parallel and 10 centimeters apart. One carries a current of 2 amps, the other a current of 5 amps. If the currents flow in opposite directions, what is the magnitude and direction of the force per unit length of one wire on the other? What is the magnitude and direction per unit length if the current flows in the same direction? This is a fantastic problem. It's got a few steps. So what do we do first? We draw a picture. First step, draw a picture. It doesn't specify whether they're going up or left or right, so pick a direction. We're just going to say if they flow in opposite directions, I'm just going to say one of them's going up, I'm going to say the other's going down. If it doesn't tell you, just pick. I could have one going to the left, one going to the right, whatever. Let's just, I don't know why I chose this. There is no benefit to one versus the other. Both will get you there. So let's call this first one current 1. I've got 2 of them, so I should label which one's which. Current 1 and current 2. If you just label them both as I, you don't know which one's which when you're plugging things in. So it's good to just put one as 1, one as 2. Call one A, call one B. However you want to do it. I tend to just use 1, 2, 3, 4, 5, however many things there are. Okay, again, right now we're literally just writing down the givens. This is how we solve a problem that seems really intimidating. We break it into small pieces. We also draw that they're 10 centimeters apart. So 10 centimeters. I'm going to go ahead and do my unit conversion now. That's 0.1 meters. The sooner you do a unit conversion, the less likely you are to forget about it down the road. Okay, and now we just jump right into the 4-step problem, 4-step problem solving process. We got our picture, step 0. Step 1, write down our givens. They're kind of already in our picture, but we're just going to organize them in a nice little list. Now we have to decide at this point what variable do we want to use for how far apart they are. You have option, distance is one of those things that there is so many variables for. Is it X? Is it D? Is it R? Just pick one. You can always go back and change it to the letter it should be. Should be in air quotes. You know what? Let's just call it D for now. I'm going to go ahead and tell you that's not what it's going to end up being, but just to show you that it's okay to just pick something. Later on, we can realize that it's not going to be D, but we'll get there. But it's just to show you don't need to freeze up on that and feel like you have to have everything perfect in step 1. We could even argue that there's more givens than that. Specifically, there's one other number we know, and we'll see that when we need it. Okay, step 2, what are we solving for? We are solving for the force per unit length. And this is where we have to use some knowledge. What is that going to look like? I want you all to spend a few moments. What force per unit length? How do I write that? See if you all can remember. We have seen this once before, maybe twice, depending on, I don't know. Definitely at least once. What does the force per unit length look like in variable form? The key to that is just to break down the words. F for force. Per means division. Length is L. Force per unit length is F divided by L. Okay. And now that we've kind of organized this, now we've kind of organized what we have, this is where we start thinking through, how do I solve this? And the good news is, if you all ever see force per length, there's only one way to find that. And it's the way we did it last time. There's only one way to find force per unit length. And you basically just think, why do current carrying wires experience a force? What causes a force on current carrying wires? That's the thought process. What causes a force on current carrying wires is what we talked about last week, a magnetic field. So then we think, okay, what is the equation for the force on a wire? It's F equals I L B sine theta. And then we say, oh look, there's that L. If I just divide that L to the other side, force per unit length is I B sine theta. I just divided the L over. Great. So now we have what we're actually solving for. We have an expression for it. And we look at this expression and we say, okay, I'm solving for F over L. Good. It's already set up for it like it's ready by itself. So that's nice. We know the current. Actually, we have two currents. So that's kind of weird. But we know currents. We don't know the magnetic field that's causing this force. So then we do another thought process of, it doesn't say there's a magnetic field in this problem. But that's where we think about the stuff we covered today. Is there something making a magnetic field? The other wire. So that's where all of it's going to start to come together. The one wire makes a magnetic field. The other wire experiences that magnetic field. That magnetic field acting on that wire causes a force. As crazy as this may seem to you all, this problem is the same, and let me actually get it set up for you all exactly right before I say which exactly it is. So this goes up, boom, boom, boom. So that's a magnetic field on this page. 1 second, I have to think through. Okay, I always have to remember what's going to happen. This is the same as the force due to two charges. Not for different reasons. This problem is analogous to this. Charge 1 makes an electric field everywhere. It makes an electric field where the second charge is. That electric field causes a force on the other charge. Except now instead of two charges, magnetic fields aren't caused by stationary charges. They're caused by current carrying wires. So this problem is the analogy of two charges. What experiences a force due to a magnetic field? A wire. What makes a force due to what makes a magnetic field? Another wire. One wire makes a field, the other experiences that field. One charge makes an electric field, another charge experiences the force due to electric field. One object with mass makes a gravitational field, another object with mass experiences the force due to the magnetic field. So one thing makes the field, the other thing experiences it. All right, experiences the force due to it. So, what's cool? Doesn't matter which one you pick. Newton's third law, for every force there's equal and opposite. So we find the force in one of them, it's the exact same as the force in the other one. So, to that end, we're just going to pick one. Let's say that this wire, current 1, is the one making the field. So what I want you all to think about, current carrying wire 1 makes a magnetic field where current carrying 2 is. I want you all to think about two things. One, how do I calculate that? How do I calculate the magnetic field it makes? What's the equation for that? Two, what's the direction for that? In fact, I'm just going to give you all the equation. I gave it to you today. The magnetic field made by a wire is mu naught I over 2 pi r. We'll come back to that. That's the equation for magnetic field due to a wire. That's the one I just gave you all a few minutes ago. But what I want you all to think about now, great, we're going to calculate that, woohoo. What's the direction of the magnetic field here due to current carrying wire 1? So wire 1 makes a magnetic field. It makes a magnetic field where the second wire is. What's the direction of the magnetic field at my blue dot? Where am I? So let's color code these. Let's make wire 1 blue. What's the direction of the magnetic field due to wire 1 at this spot? We'll just call it P. We'll need it eventually. So your thumb points up, your finger, current carrying wire 1 is up, your fingers point towards point P, your palm says that the magnetic field is into the page. Wire 1 makes a magnetic field into the page where wire 2 is. It makes a magnetic field, and let's just call this B1, the magnetic field due to wire 1. And now that we've done that, you can basically pretend like this wire doesn't exist. Once you find that, it's just, hey, find the force in a wire, whatever, do the magnetic field. So let's go ahead and take this whole thing, move it to the other side. And yeah, this is a great problem to kind of think through. This problem takes all the ideas and puts them together. So, wire 1 makes a magnetic field. Let's just go ahead and calculate it. So remember, there's a couple things I told you all. I said there's one more given. It's mu naught. We know mu naught. We didn't even know we needed mu naught. We need mu naught. So mu naught is 4 pi e to the minus 7. Wire 1 is making the magnetic field that the other one experiences. 2 pi, and this is where I told you all, we called the distance between them d. We can now see what that variable, what's probably more appropriate to write it as, r. We're finding the magnetic field 0.1 meters away from it, where the other wire is. So let's go ahead, that's r. It's okay to have it as a different label as long as down the road you realize, oh, okay, it's actually this. Plug that on in, that spits out a number. So the current carrying wire, wire number 1, spits out a magnetic field 0.1 meters away of 4e, 4 times 10 to the minus 6 Tesla. It's very small. Remember, it's hard to make strong magnetic fields. You should not expect to have a strong magnetic field due to a single wire. It's going to be really small. Okay, great. We got B. What was the point of this? This problem did not ask us to find the magnetic field due to wire 1. This was a step in the process. Our end goal was this. Find the force per unit length. So, if I want F over L, wire 2 experiences the force due to the magnetic field from 1. And then we look at that sine of theta. Theta is the angle between the magnetic field and the current. If my magnetic field is into the page and my current is down, it's 90 degrees. Again, most of these problems, y'all, theta is going to be 0 or 90. Unless I specifically say, find the angle, for like a very simple example. So sine of 90 is going to be 1. So if we just put in these numbers, F over L equals 5 times 4e minus 6. And that's it. Which is really nice. It's just 20e minus 6. And don't forget your units. Newtons. Great. That is the force that wire 2 experiences due to wire 1. Wire 1 makes a magnetic field. Wire 2 experiences the force due to the magnetic field. And the exact opposite is true. Wire 2 makes a magnetic field. Wire 1 experiences the force of the magnetic field. And there's a couple questions that we have to follow up on. One is, I told you all it didn't matter which wire you chose. Why? It's all multiplication. Every step we did here was multiplication. There's division too. But if you just replace this with 3, so if you find the magnetic field due to wire 1, due to wire 1, we put that 2 there. But we put the 5 here. If you do the exact opposite, you put the 5 here and you put the 2 here. So let me go ahead and show you the master equation. If we just did this in one big go, if we said the force per unit length and I plugged this giant thing in here, I want you to show you why it doesn't matter. If we plug that giant thing in there and we kind of built the master equation, the force per length due to one wire on another, it's I2 times 4 pi e minus 7 times I1 over 2 pi r. I2 is times I1. Who cares what order they're in? 2 times 5 is the same as 5 times 2. This is also proved by Newton's third law. For every force, there's an equal and opposite. So if wire 2 experiences a force of 20 times 10 to the minus 6, wire 1 experiences a force of 20 times 10 to the minus 6. And this leads us into the last thing we have to do. What's the direction of that force? Are they going to get pushed apart? Are they going to get pushed funkily? Go ahead, y'all. See if you can figure out the direction of it. Wire 1 made a magnetic field into the page. Wire 2 had a current going up. Use right-hand rule number 1 to find the direction of the force on it. If I have a magnetic field into the page and I have a wire carrying current down, what's the direction of the force? If I have a magnetic field, we are looking just at this situation right here. I've got a magnetic field into the page. I've got a current carrying wire. Current's going down. What's the direction of the force? So, remember you got to flip things up. My fingers are going to point in the direction of current. So my fingers point down. I then point my palm. What is this? Fantastic. Okay. My fingers point down. My palm points in the direction of the magnetic field that's into the page. The force is to the right. Away from it. Fingers point in the direction of current, palm points in the direction of the magnetic field, the force is away from it. Okay. Fantastic. So remember, this wire, so for those online, fingers point down, palm points in the direction of the magnetic field, my thumb points to the right. The force that this experiences is to the right. And I want you all to spend a few seconds. If this one experiences a force to the right, which way will the other one experience a force? And I'm going to give you all a shortcut. Newton's third law. For every force, there is an equal and opposite force. For every force, there's an equal and opposite. So if wire 1 pushes wire 2 to the right, wire 2 will push wire 1 equal and opposite. It'll push it to the left. Yeah.
If you wrote it side to side, it would be down.
Yeah, up and down. Yeah, so in this case, the problem says, well, the wires, let's see what the wording was exactly. The problem said, what is the magnitude of it? So it just asks for the magnitude. Oh, no, it says direction. We would just say away from each other. No matter which way you oriented them, they're actually going to push away from each other. So this connects back. Remember I told you all at the very beginning, and this is where I had to pause and think about it. This is analogous to two positive charges. One makes a field, and they repel each other. Okay, and it's a good exercise for you all as well. I'm going to quickly just give you the answer to this. So if we wanted to go through the steps and prove this, we would find the magnetic field. So let's make wire 2, let's make it green. So if I wanted to prove this, if you want to prove this to yourself, and it may seem silly, like why would I want to spend the time and energy? It's a good exercise. Wire 2 makes a magnetic field into the page where wire 1 is. You can prove that to yourself. Right hand rule number 2. Thumb points down, fingers point towards it, fingers swing in. If I have a magnetic field, so this is B2, if I have a magnetic field that's into the page, and I have a current carrying wire going up, just test the rule. Fingers go up, hand points into the page, thumb points to the left, and ta-da, we prove Newton's third law still works. So you can kind of prove it for yourself. All right. Mathematically, we didn't have to do anything crazy. So the hard part of this problem isn't the math. It's connecting the concepts together. So this is a fantastic problem to test if you understand the concepts. You have to do the math to find the magnetic field due to a current carrying wire. You have to do the math to find the force per unit length on something. You have to use both right-hand rules, and you have to do it all together. So this is a great problem to try to solve without looking at the solutions the whole time. Again, that's always the key to studying these, y'all. If you just look at my solutions and say, that makes sense, that makes sense, that makes sense, you're kind of cheating yourself a bit, because it's kind of like, gosh, I don't want to inflate my ego. It's like watching someone that's a good painter and saying, oh, look at them, like doing all the brush strokes and stuff like that, and then you try to draw it and it looks who knows what. I say this, I'm a terrible painter. This is much easier than painting, in my opinion. You may have different opinions. A lot less steps to this than a painting. Yeah, make certain you all can go through this. Only look at the solutions if you're stumped. And then if that does happen, you should come back to it at some later point and try it again. As many times as you need to until you can do it yourself, because at the end of the day, that's what you have to do on the test. You have to be able to do it yourself. Okay, I'm going to quickly mention there's 2 parts of this problem. It said to have them pointed opposite directions and have them point the same direction. Fun fact, y'all, the problem basically is the same, and there's only one tiny difference. Well, tiny, matter of perspective. So if we have current carrying wire up, so same everything. Same everything, but instead of being opposite directions, now they're the same direction. They're still 0.1 meters apart from each other. And it says find the force per unit length and find the direction. The math is identical. The math didn't care about the directions of the things. So the answer for the force per unit length is literally the same exact number. Everything is the same. So what does change? Spend a few seconds and think what will change then. If the force doesn't change, what does that leave? The force, the direction of the force changes. The direction of the force changes. So to prove that to you all, wire 1 still points up. So that means it makes a magnetic field still into the page. That has not changed. Go ahead and find the direction of the force on a current carrying wire. Current's going up, magnetic field is into the page. What is the direction of the force? Do the right-hand rule, number 1, and try it out for yourself. I'll wait a bit. No better way than to do it. Right-hand rule is one of those where you literally just gotta twist things around. So, current points up, palm points into the page, thumb points to the left. Fingers point up, palm points into the page. So this will experience a force to the left. If we do the exact, so current carrying wire number 2, that's going to make a magnetic field out of the page. Again, good exercise for you all to prove to yourself. Right-hand rule number 1. Do the same thing. Right-hand rule number 2. And that will experience a force to the right. For every force, there's an equal and opposite. If wire 2 pulls wire 1 to the left, wire 1 pulls wire 2 to the left, wire 2 will pull wire 1 to the right. For every force, there's an equal and opposite. So what's the analogy of this? This is like having a positive charge and a negative charge. The electric field, due to the negative charge, will pull this guy, the positive charge to the right. The positive charge will pull that one to the left. Pull the positive charge to the left, negative charge to the right. But don't use that to solve it. But that is kind of the analogy. Depending on which way the currents are, they can attract. Depending on which way the currents are, they can repel. And I'll tell you all, again, this is a very good problem. You can expect that I'm going to ask you, hey, there's 2 wires. Are they going to attract or repel? Cool. All right. So, fantastic. That's kind of one of the trickier problems because it combines 2 concepts together. Okay, so we got a straight wire. There's other geometries of wires. Wires do more things than going in straight lines. Honestly, there's only 2 things they do. Straight lines, and we'll see this next one. We're going to build to it. So instead of the wire being straight, let's do something absolutely wild. Oh my gosh, we're going to bend it slightly. Yay! An arc of wire. An arc of wire meaning it's not a full circle. It's just like a arc, a piece of that circle. The equation for this is mu naught I theta over 4 pi r. This should look really familiar, like it almost looks identical to the last one. There's only one tiny difference, well, 2 tiny differences. The last one was 2 pi r on the bottom, and this one has theta. Theta is the angle of the arc. So you can see the picture here. Theta is how much of an arc it is. And we're going to unpack what happens as that arc grows to being a full circle. What I really want to point out to you all, though, this arc is measured in radians. You cannot use degrees for this. You cannot use degrees for this. So if this was a quarter of a circle, you would not use 90 degrees. You would use pi over 2. Okay? I'm not going to be really mean with this. I'm not going to check if you all have your units, if you have radians memorized, stuff like that. But just know that you do need to use radians, not degrees. If you put in degrees, this just doesn't work. This is why radians are actually a better measure of angle than degrees, but they're just really funky. No one's going to be teaching elementary schoolers 2 pi radians in a circle. They're going to be like, what's pi? And then you say it's an irrational number that goes up. It's just terrible. All right, so you tell them 360 degrees in a circle, and it's way easier. But the reality is radians is more useful. 360 is just an easier number than 2 pi. All right, so building on this, again, mu naught I theta over 4 pi r. We're going to take this to its kind of conclusion. What is the magnitude of the magnetic field at the center of a half circle of wire? And I'll even write the equation on here for you all, the one that I just wrote. And okay, so I said I wasn't going to be mean. I'm not going to ask you something like this in the test. But for a clicker question, I don't feel bad. B equals mu naught I times theta over 4 pi r. All I'm asking you all for here, what is theta for half a circle in radians? And I'll even be kind. There's 2 pi radians in a full circle. So go from there. So it's basically, yeah, just what's the angle? What's the angle in radians by half a circle? What is that angle? All right, we'll go to 120. There's no math here. Okay, I guess there's like tiny math. All right, and close it out in 5, 4, 3, 2, 1. So, if a full circle is 2 pi, half a circle is pi. So this angle is pi. So then you just plug that in. B equals mu naught I pi over 4 pi r. Look at that, the pi is gone. Fantastic, how convenient. And there's our answer. Mu naught I over 4r. Nice. So, different answers, but there you go. Good one to look through then. Try for yourself. Okay? The next question to you all, the natural next step. What is the direction of the magnetic field at the center of this wire? And what is my recommendation to you all? You're like, what do you do? Just pick a piece of the wire. Pick just this spot. I have current going up. What's the direction of the magnetic field? If I have a current carrying wire going up, what's the direction of the magnetic field at some spot to the left of it? And if you're like, but I don't like the right side. Okay, then pick this spot. And you're like, I don't like that spot. Okay, pick that spot at the bottom. It doesn't matter what spot you pick. It all works. So pick one of those spots, whichever one makes you feel the coziest. Point your fingers in the direction of current, your thumb in the direction of current, point your fingers at the spot P, and then your palm tells you the direction of the magnetic field at the center. All right, we'll go to 115. All right, so 5, 4, 3, 2, 1. And we'll close it. All right, so to answer this, who cares what spot you pick? Let's pick the bottom. Thumb points to the right, finger points towards point P, magnetic field is out. All right, pick this spot. Thumb points up, fingers point towards P, palm points out. Oh, let's pick this spot. Thumb points up to the left, finger points towards point P, palm points out. Literally, you can just trace this thing with your thumb. Keep your fingers pointed towards point P, and it always points out. So this leads us to, if something's going in a circle, this is the shortcut, y'all. This is right-hand rule 2.5. That you do not, if this just confuses you, you do not need to use it, but we'll apply it to this problem. If you have a loop, this only works for loops. It only works for loops. If you have a loop, curl your fingers in the direction that the loop's current is going, and your thumb points in the direction of the magnetic field. So if we look at this last problem, if you curl your fingers in the direction that the current's going, inside the loop, the magnetic field points out of it. Right-hand rule 2.5 is just a shortcut. If you have a loop, you can kind of curl your fingers around and the thumb points out. Curl your fingers around, thumb points out. Otherwise, just pick one spot on the wire. Do normal right-hand rule number 2. Again, you can see it here. Curl your fingers in it, thumb points up. If the wire's going the other way, curl them the other way, thumb points down. If remembering this many if an extra right-hand rule causes too much stress for you, don't worry about it. But it is a nice shortcut, especially as you solve more and more and more of these. And the rules are really simple. All right, there you go, y'all. So good. Next time, we're going to take this full circle, because it's a circle. What a great joke. All right, have a great one, y'all. Oh, and joke of the day, because to the person who stole my Microsoft Office license, I will find you. You have my word. There you go. Tell your friends. All right, y'all, have a good one. Good luck with all these right-hand rules. It's a good time. If you make mistakes on, like, the right-hand rule is the hard part, in my opinion. The math is, it ain't bad. No, nothing too crazy yet.